Then welcome to the last real lecture on causality for AI and ML. Today, I will be talking a bit more about research we do in our lab here at Darmstadt. And as already announced, next week will then be more of a Q&A recap of the whole lecture and so on. Yeah, let's start with the lecture. And so maybe to go back to the very first lecture we had, that we had this quote that machines' lack of understanding of causal relations is perhaps the biggest roadblock to giving them human-level intelligence. And already there, I highlighted this understanding of causal relation. And so far, what we have done is most of the time looked at causal models and tried to infer causal quantities within these fixed static structures. But I would argue that to really understand how the world works or how mechanisms evolve, we cannot only reason within those models, but we need to understand how causal mechanisms evolve, how they emerge, under which conditions they maybe also vanish. So we also need a kind of tool that lets us model these conditions under which we can assume a causal link to be there in the graph or not. And then we already talked about LLMs, whether they are causal parrots. And this is really the kind of counterexample, although modern models get better and better. But in the simplest case, you present some model, maybe an LLM, maybe some other machine learning model with some data, and it memorizes the causal relationships. If we are lucky or set up the training right, they get it correct. And the question then really is, do they still understand what that means to have a causal relation between any two variables? Did we expose them to enough information that, for example, if I now intervene or maybe some other factor prevents this causal link to appear or to propagate, can they really understand under or in which situations we can apply those rules that we see in the data, and in which situation we should reason about the absence or assume the absence of a causal link? And as humans, it's most of the time maybe not easy, but we use a lot of background knowledge, right? We know how physics work, how everyday things behave, but these models usually don't have all that background knowledge. Maybe now with LLMs and those video generation models, it's becoming better. But somehow, most of the time, we train our models on a fixed static data set and then pray that the distribution that we test on or that we employ the models on is roughly the same as the one we showed them in the training. So yeah, that's for LLMs, and really the same thing can be said about SEMs, right? We have these cool models, and we are able with due calculus to infer some quantities, some causal effects, maybe even interventions and counterfactuals. But these SEMs themselves might change, and in these cases, our predictions might not hold true anymore. So the question is, can we have causal models or some models in general that help us to reason about causal change? So under which conditions these models become different, some edges emerge or not. And yeah, we propose this concept or model of meta-causal models, which I will talk about in this lecture. But first, maybe we will have a look at a phenomenon which is not that often discussed in lectures, but I think it's quite important because it is something that usually or very often appears in the real world. It can also show up in data, but particularly when talking about type causal inference, so where effects always are there or not, it's not discussed that much because it violates or can violate some of the assumptions that we have. So the idea is really this contextual independence. which is basically a special case of conditional independence, meaning that, okay, usually the key and the gas pedal, they are somehow related, they influence the speed. But if I turn off the car, if I forget my key, I can press the pedal as much as I like, nothing will happen. So under particular variable settings, variables become independent of each other. Although if I now look at the whole distribution, I would infer that this relation is there, right? Because I have some points, some data points where this relation shows up. And depending on the probability of those two scenarios, I might just say, okay, this case, it's probably due to noise or whatever, right? It will go into my exogenous variables if I'm not careful enough. But yeah, if we want to have like good causal models, we should probably search for those conditions where it's not only, okay, is there always or never a link between two variables, but are there special settings of those variables that can yield those dependencies or independencies? And generally, this is written as like similar to conditional independencies. A is independent of B given some setting of some other variable. Usually we assume if we talk about contextual independencies that there is also variable setting where they are dependent, because otherwise we just have the conditional independency. And the problem then is that these things can get a bit more complex. So this example I really like because it can show up in maybe production processes, in games or whatever. So these variables, like the gripper position and this block position, they are maybe most of the time independent, or for some special configurations of the gripper and the block, they are dependent. So particularly whenever the gripper is like close to the block, then we might see a causal relationship between those two. And the problem here is that it's not like a condition on some fixed constant of one of the variables, but it's rather a function of the gripper and the block position. So depending on where the block is, we need to adjust the gripper position to get this dependency or independency. And that's already then much harder to find. But the thing is that our causal models usually don't even have like this notion of functions that conditionally turn on or off those edges. So yeah, in this lecture, we will be talking about meta-causality, and there's also a notion of meta-causality in like philosophy, but that's not what we are talking about here. It's really about models that reason over SEMs. So we look at an SEM and really try to find those conditions under which causal edges change. And yeah, this can be used for some reasons. So maybe we are interested in the stability. Maybe we are interested also in like critical situations. So we saw the whole population, but we are now interested in a particular setting of variables. And for example, in actual causality, want to know whether my causal link will be there in this particular scenario. Maybe if we actually intervene or like our agent intervenes in some environment, we want to make sure that our interventions do not push some of the values into like weird regions or domains where some of the causal links break down. For example, in physical systems, if you have like structural links, you might see an independency if you put light loads on the structure, but if it gets too heavy, maybe it will first bend, but then at some point break, which is then really a qualitative change in the causal relation, which then also usually can't be recovered afterwards. Yeah, then it's also about system dynamics. So how do these states of structural causal models, like different structural models, evolve into each other? Can we go back from one state to another? So can we repair or make some causal links reappear, or if we lose them once, they are broken. For example, in this some bar or whatever breaking, it's hard to repair. And then what we will see next is an example about attribution, something we talked about before, that might give a different answer or like differentiate between two answers. So the first example here is really this: you have two robots, and robot A decides to keep a constant distance to robot B. And we now ask what causes A's position. And if we were to look at our structural causal model, we would see something like this, right? So the position of A is some function of the position of B. And now if we trace back this whole thing, we would say, well, somehow B is the cause for A's position. But if we think about how this model came up, we see that actually we have A's policy that somehow established this link in the first place, right? By following B. So we could also attribute A, or we would like to attribute A itself for establishing that relation in the first place. And here again, we have this setting where we have a position of A, the policy of A, and the position of B. And in classical causal models, you would usually draw an arrow from the policy of A to the position of A, and then have some structural equation that looks at the two cases where A follows B or where it's like standing around. And depending on that, you have those contextual independencies. The problem with that is that if you are now in a more complex setting where you have a lot of different objects, A could possibly interact with all of those objects. So in your final causal graph, you would have all those links, right? And okay, maybe you say, now I'm looking at actual causality. I only look at the link that is currently active, but then it, like, you don't have a notion which other scenarios are possible. So this policy establishing this link or not, at least we argue that it's qualitatively a different type of relation, because it's not the other way around that B can somehow activate this link for A, but it's only in this other direction. And somehow we want to capture this. So we will talk about models that really have this mechanism that learn a function or possess a function that tells us when some causal links are there. And so a bit more formally, if you think about how to formalize these meta-causal factors, it's really that if I fixed all other variables in my environment, and then for some variable, I can have a different value of my meta-causal variable. So meta-causal variable, again, is this policy of A, for example, where I have those blue arrows that go onto the edges and not on variables themselves. Everywhere where I can have a different causal value and a different type of edge emerges in my causal graph, that I call a meta-causal variable. And I think the first part might be okay within like standard SEMs, but these types of edges is maybe something that we need to discuss, because so far we only looked at structural equations, but especially in language and so on, we might want to look at qualitative types of edges that, for example, not look whether, I don't know, in a linear relation, I have a factor of, I don't know, 2.5 or 3.5 or whatever, but maybe I'm interested in like qualitatively, is there an edge or is there no edge? Or maybe is the factor that I have in front of the relation, is it positive or negative? So is it a suppressing or reinforcing effect, for example? For this, we introduce or has been introduced already in some prior work. But here for SEMs, it's really that we want to have a function. We call it a type encoder, but it's like really a user-defined function that looks at all the structural equations and then assigns some sort of qualitative type that we will use to reason over. So the reason here is that in the end, we might not be super interested in the particular factors that go in front of the edges or connect those variables, but really if there is an edge or not, and then how do those models transition into each other. So yeah, it's this classical example of temperature increases with altitude. I don't know, caffeine intake increases alertness, but depresses sleep quality and so on. And in the simplest case, we really get back our adjacency matrix, right? Where we have a special type that always tells us, okay, there is no edge or no causal link present. And in the other case, that there is a causal link present. But then we can have arbitrary, like fine-grained type encoders or types that tell us, okay, there is a positive or negative factor associated with the edge. Or in the most fine-grained case, we really say, okay, there is a type for every possible factor here. But I think usually these somehow broader types that somehow relate to a question that we want to answer in the end are best, because we might want to have, I don't know, a handful of structural causal types that then build these causal models that we can reason over. Basically, what we then do is we take our type encoder, we take all of our samples, and this then, of course, assumes that we see different different causal models in our data or can identify them. And we say, well, every of those, now not adjacency matrices, but type matrices that form a different causal graph, they are a meta-causal state, right? If I look at a particular sample, what is the meta-causal state that my system is currently in? Of course, this somehow assumes that we can trace back from our samples to the meta-causal state. So if we look at it from a probabilistic perspective, it might be that I see a sample and it could be emitted or produced from two different meta-causal states. So inference can be a bit tricky, but conceptually, we just assume for now that we have this way where we can trace back all these states that we have. And then we want to see how those things evolve or transition. And for that, we make an additional assumption, which basically is that we have some underlying mediation process. And I think this is really what differentiates then these meta-causal models that we will see in a bit from SEMs, because here we assume some sort of Markov process, like, I don't know, a real world process, some sort of video or whatever that does not need to be causal. But then we apply a causal abstraction or like a general abstraction that from those videos, from some images, infers some causal variables. And somehow we need to learn this transition function of this Markov process. And then we will try to also apply our causal abstraction here. So this is really on a high level because obviously the causal abstraction is usually defined only over the variables. But let's say we can do that. So these variables are actually random variables, so they are sort of functions. And then we, in theory, would also get our structural equations. So the thing is really that our causal models are not like the ground truth, right? If you look at the book of Y or Causality or like some other papers, they always talk about, okay, there is this one true causal world model. And the question is, does that really hold true? Because there are so many things that just aren't causal, right? Or that are trivially causal, like how physics evolves, the causal models that we get in the end are really abstractions of this real world, right? They are much less complex than the things we are trying to model. And usually every approach that we try to like model everything in terms of like a causal variable is somehow bound to fail. So yeah, the idea is to have this underlying process, apply causal abstraction or general sum abstraction, and then we can use this process to propagate forward in time. And if we can define this causal abstraction in a good way, we should see that with this process advancing, we also see our causal models change. We see causal effects arise. So this is then maybe a bit closer already to actual causality, because now we are always depend on the state of the system. So it's not this like very general type causality, although in every moment in time, we get a particular SEM that is currently active. And then there is a lot of formalism. Basically, it's the things I've told you. So just briefly, we have a sort of identification function that identifies those causal states. As I said, the state of the underlying environment is important. Then we look at every relation, so every cell in this matrix between every variable xi and xj. And particularly, we have those type encoders that are user-defined. So it's really up to you on what you would like to focus in a particular setting or scene that then identify from the image I see, from the video I see, those causal variables and the causal relations. And yeah, then we have meta-causal frames, which bind all of this together. You don't need to care about that much. But the important thing then is we define meta-causal models, which basically are probabilistic state machines, or you can also frame them as Markov processes themselves. Basically, it tells us, okay, if I now see a particular state, so a particular structural causal model, I observe some additional image of my underlying process, what will be the next causal graph that I will transition into? And this can either be deterministic, or it can again be a like probabilistic function. So really the idea is to somehow get away from this Markov process and really only reason over the state of the SEM, have some sort of like observed vector, and this observed vector then can be in the state of the Markov process, but through this abstraction, we might be able to also lift it into the realm of the causal variables. And then really over time, have these models that predict, okay, which edges will be there in the next time steps, which edges will vanish. So maybe I see my robot arm moving away from the block, so this causal link will break, or I see it moving towards this block, so it will be there. And because we added those types to our model, it's really reasoning about qualitative change. So initially, all of this was really motivated from our works on causal parrots and with LLMs, where humans usually talk in terms of, okay, A suppresses B, A causes B, whatever. It's not that we communicate the actual structural equations, but we communicate qualitative causal links. And so we also want to talk about how systems change qualitatively, like if something breaks or not. We aren't most of the time interested then in the way how much it breaks or whatever that means. But yeah, if you leave away all the types, you say, well, every of my structural equations, how they can be defined, is a causal type, then of course you are back at your normal SEM level, where also all those factors attached to those equations matter. So we will have this one example here, which is on self-reinforcing stress, because now you could say, well, I have my causal model, I have these strange meta-causal processes, and yeah, isn't it enough to have some sort of like type variable that I might want to introduce into my SEM, which depending on the state of this variable just tells me, okay, if this state or type variable is 1, then I have causal effects A and B. If it's 2, then I have some different SEM and so on. So can't I just condition my SEM on some external variable and just make these causal relations emerge, or like reason about whether they will be there or not? And the answer here is that there are some cases where the structural causal equations, they stay the same, but the type of the system can differ. So yeah, assume a person that has maybe a busy workday, and he or she has like some internal stress level and some external stressors. So depending on how the day goes, at the end they might to be able to relax a bit. And if it was very stressful, maybe they think about things after work and they stress themselves even more and more. And what we modeled, so I mean it's still a toy example, but the thing here is that we model the stress level of the current day to the stress level of the next day. So how the systems transition. And there is this sort of tipping point where if we go over a particular level of internal stress, they will get into this self-reinforcing loop, right? Where they stress themselves even more and more, and it like doesn't stop. And otherwise, if we are at low stress levels from one day to the other, they will reduce again. But the thing here really is that this structural equation, so it's modeled with a form of sigmoid, stays the same in both cases. So really it's important to not that like we can't have some external variable that just tells us, okay, you need to set these or that structural causal equations, but really we can have the same equations in our causal model, and the context matters. So the state of the values of the actual variables in our system. So in this case, we can get 2 or 3 meta-causal states, where 2 of those are really the self-reinforcing behavior. The other one is this suppressing behavior. So right, we assume, or just assume there's always this external effect on like the internal stress level. And then this internal stress level either has a self-reinforcing or suppressing effect. And theoretically, there is this third model where it's really at this tipping point where it keeps the balance. Then if we talk about those type encoders, like how could we set this up in a structural or in a meta-causal model, we can say, well, I have this tau, which basically tells me, okay, there is no effect from S to E. There's no effect from E to itself. The effect from E to S is always there. And for this thing from the stress level onto itself, there we need to look at basically the sign of the second derivative. So yeah, basically it boils down to, under this causal model, are we in the upper half or the lower half of this domain? Right. So yeah, in this setting, we look at the sign, and sometimes it's the zero influence, which is exactly this middle thing, which is then the things we usually not draw. So this was a simple example. Then we can also have some meta-causal state inference, where we say, well, I look at those 2 agents or robots again, and I might be interested in doing things the other way around, where I say, well, whenever I observe a particular setup of variables, I can infer the state of the system. So this is like reasoning about maybe agents' behaviors or intention. If I say someone going to the kitchen, maybe it's not like clear whether he or she will open the window or get a snack. But as soon as I then see them approaching maybe the fridge, then I know maybe or possibly the policy is to get a snack. And here it's the same thing. So it's a lot of formulas for basically saying if A faces B, then I assume, so it's modeled as a game of catch, then A is following B. And the other direction or state that we allowed in the setting was, okay, that they are facing the exact opposite way. So then B would be chasing A. This just is this dot product. I think it should even work in the 2D case, which tells us, okay, depending on the facing direction and the positions of the two agents to each other, which of those two is chasing which. Here, this then was also a point that we are not like really haven't figured out very clearly, or that might be improved in future works. What this tells us that in some cases we can trace back from this configuration of variables onto our meta-causal state. But again, it's not really clear under which conditions this high-level state can be uniquely identified and in which settings, if we know our like some meta-causal state, when it really introduces causal effects, right? So the question is, I know my meta-causal variables, but those meta-causal variables are formed by an abstraction of my underlying process. And now I can intervene like virtually on my causal variables, but will these interventions that I do, will it backpropagate to my underlying process? So is my causal abstraction really strong enough, assertive enough that I can invert it and that my causal variables really map back to this underlying state, or will something weird happen? So it's basically on these conditions of my causal abstractions. For all of those previous examples, what we usually assume is this meta-causal predictability, which basically tells us, okay, the causal variables that I see in my model are enough to predict the causal type. And if I change my causal variables, it also somehow alters the trajectory of my meta-causal model or my system, my underlying system. Basically, what this tells us, okay, if I intervene, if an agent acts, like it's a sound, it's a maybe constructive causal abstraction that is strong enough to truly model what the underlying system is doing. Right. Then we can do something more analytical, which might not need this like very strict assertive causal abstractions, but it's more like looking at statistics. So we can have meta-causal analysis, which maybe able to like let us answer particular properties of my current system. So how stable is my current state? How likely am I observe a particular state in my system? Maybe also in dynamical systems, if I let them run, how likely is a particular meta-causal state to merge? So maybe I'm interested in that for, I don't know, medication or treating a patient, that I do not want to have the situation where I need to intervene, so give medication for the rest of their lives, but maybe I'd be happier if I can somehow give a medication that suppresses some bacteria, some symptoms. And for that, I don't know, my immune system takes over and establishes a particular causal link that will always, so for vaccinations, will always suppress those viruses or bacteria whenever I see them, right? So somehow it's also about, okay, I can maybe always force my system into a particular meta-causal state via interventions, but those interventions might be costly. So I want to transition my system in a state where a particular causal link establishes that like takes the role of those interventions that I would otherwise need to like introduce externally. Yeah, and then also with regard to stability, I can transition through different or chains of meta-causal states, and maybe not all of them are safe or ethical or whatever. So it's then if I look at my meta-causal models, maybe I can take different pathways through the same state that I want to reach in the end, but maybe some of those paths are like safer, more ethical than others. So yeah, I maybe want also to consider these types of questions. So what you see here is basically a fancy way of saying, okay, record all these statistics. We observe some data set. We say, well, I assume somehow that my causal links, that's how edges emerge or vanish, that it roughly behaves the same over all of those data points that I have, and then for prediction, possibly also in the future. And it's really doing statistics. It's saying, okay, I have my data. I take my identification function to figure out or like either deterministically or get a probability of which kinds of MCFs I'm in. Then I advance the system. So this really needs either that I have a second data point from the next day or the next month, or I have this meta-causal predictability where I know, okay, I can just advance the model within my structural equations to simulate or predict the next data point. And then for this next point, I also predict the MCS, right? And if I have those pairs, I can just compute the transition dynamics. So what is the probability from going from one state at the first data point of the pair to the MCS of the second data point in the pair? Yeah, maybe we will look at a bit more complex example. So the idea is exactly this medicating flu. So we have some virus exposure that induces a fever. This is, of course, somehow conditional on the immune strength. If we get fever, of course, our body temperature rises. And in some cases, if it's getting too high, we will give some medication. Now, if we think about all the ways how causal effects can emerge or like how things can influence each other, we might say, well, maybe there is no exposure or only low exposure. Then we also say, well, the immune strength, it's nice to be there, but if I have no fever, maybe like it has no actual effect. So these two errors might be there or not, or at least maybe they might be in a high or low state. Then conditional on or contextual on the fever that I have. Of course, it influences body temperature and medication. So this tells us, okay, I have no fever, I have mild fever or high fever. And then the medication really is a yes or no decision. We assume that in this setting, at least, medication, of course, reduces body temperature, but it might also somehow impede the immune system or the development of the immune system. Basically, in the end, we identify if we simulate this for virtual patients and we take sample points where under some policy we give medication or not. We will see, okay, I have basically these three states that I focus on. So there are a bit more, but like those are the ones where this medication somehow plays a role. So either the patient is healthy with then no fever, or rather no fever, therefore I give no medication. Then I have maybe mild fevers, so I do not need to give medication. So this edge might be active, but medication is still at zero, so those are not existent. And then I have strong fever where I need to give medication. Then there is, like, if you think of it in terms of like all possible combination, of course, no fever and giving medication, which we then never observe in the data. So we exclude it from our analysis. Finally, so there's a long tradition also in longitudinal statistics. So if I give some medication to some patient over like a span of years, how are like the average population statistics? How is the like average outcome? Does this medication help or harm? And here we did also simulate two things. So one, medication A has a higher effect on the fever symptoms, but also impresses the immune system more. And the other one has a lower effect. Still, we assume it is sufficient, and there goes a lot of like consideration in it. If you were to propose a study, like you would have to think about, okay, is it okay that I always give medication A or B? Because what we looked at in our system or in our simulations was, okay, is the long-term outcome? Which one is better for the patient? But in some cases, the short-term outcome is very important because like if you have very high fever and if you give medication B that has only a lower effect, maybe that's not okay. Maybe you need to reduce the fever now and not like gamble on, okay, the patient will be fine. But here we assume, okay, both of these are fine, and A has a higher effect on body temperature and immune strength, and B has a lower one, but both are equally good. Maybe then there are other factors such as cost, and somehow we want to decide which one to use. Again, yeah, we simulate all of our patients. We have a random exposure of viruses. And then on some policy say when to give the medication, how much it suppresses the immune strength, and it always treats the body temperature. Basically, as I said before, these meta-causal systems or models really can be seen as Markov processes. So we simply have these transition dynamics or probabilities. And then if we consider what would be the notion of an average treatment effect in this kind of setting, then we can look at meta-causal ATE in the way that it is the difference between the two treatments. Usually ATE is defined as treating versus not treating a patient. So here we have two different treatments, but the same thing could be done with, okay, I replace any of those two scenarios with a setting where I never treat the patient, which obviously wouldn't be good because then the patient probably isn't fine. Yeah, but basically for an ATE, we get, or the standard ATE, we get a single number that tells us I have this or that effect on some sort of variable. And for meta-causal ATE, I really get these differences in those errors, right? So if you look on the probability of, okay, I have in 1 year basically no fever, and I also need no medication, then it's really this difference here between 30 and 52%, which is then shown here. And what we see basically is that if I transition from medication from A to B, really it's that with the milder treatment, the patients get less into this fever causal graph or setting where they need treatment. And if they have it, they are much more likely to transition away from it. Because if I have this very strong immune system suppressing medication, at some point the immune system doesn't develop enough. So every virus exposure basically results in the fever that needs to be treated. So this is really then this consideration. okay, in these cases, I can still treat the fever and assuming that the patient will be fine in this setting, but it's a much higher cost because every time I need to buy this medicine, I need to treat the patient and so on. I always need these external influences on my system. Whereas if the immune system can handle it itself, then I'm basically fine. Yep. And then a similar thing just to show you possible other application, which is maybe a bit more in terms of reasoning. But I can also look at judicial decision making. So I have a judge that somehow notices, okay, as sessions go longer and longer, he or she tends to make like biased decisions or wrong decisions. And this can be modeled as an SEM. Basically tells, okay, at the start of the day, I have a particular case pool of cases that are somehow complex and we just model it with some sort of number for. Then I have a scheduling function that tells me, okay, in which order am I to work on those cases? And in the end, I make a decision, which may be biased or not. And I have this fatigue value that just increases over time. So we assume here it's like independent of whatever case I'm working on. So if we look at meta-causal models, or if we reflect on the scenario itself, we see that decision bias somehow gets introduced by a combination of fatigue and case complexity. So basically down here, decision biases arises if the complexity and fatigue go above a particular threshold. And then I want to reason about, or maybe some agent wants to reason about, okay, how can I prevent this? I might not be able to intervene on fatigue, but maybe I'm able to intervene on the case complexity. And basically how I do this by changing my SEM. So really looking at a different schedule, which schedules the hard cases first. So I mean, in terms of reasoning, in terms of logic, it might be super simple, this example, right? But the thing here is that, yeah, if you consider SEMs themselves, you are bound to reason within those structures. And depending on which interventions you are allowed to make, you might not be able to break out from the scenario where at some point the judge makes some biased decision. So this is maybe also more of a motivating example where we say, okay, I really want to reason about how I can change my SEM, what I can alter, and not only in terms of my values of the variables, but how I need to alter the system in terms of the structural equations that I have. So can I transition the system into a different, in this case then meta-causal state, where the scheduling function is a maybe qualitatively different type, for example. And the result then basically is, okay, if I order these things, I get unbiased results. Meta-causal reasoning is more of this structural, qualitative type of models and reasoning, whereas classical causality usually looks at individual like effects within a fixed model, although interventions obviously somehow change these relations. So every time I intervene on a variable, of course, I am altering the meta-causal state, right? Because I'm removing all the edges to a variable's parent. And then maybe for this last lecture, more general outlook. So what we are working on at the moment, or particular I'm working on at the moment, is to somehow grasp this thing of genuine causal reasoning, which is really this type of stuff we discussed before with meta-causality. So also look at why is there a causal edge, under which conditions does a causal edge emerge, and maybe can I reason about what happens when I change some values in the system, how will the system evolve, and in which causal state it will end up eventually. So We talked about all of this also in previous lectures. So it's really about reflection and adaptation. So we need to be not only reason within our causal models, we need to have some models, and natural language really is a good way because it lets us talk about causal quantities. We need models that are able to express these assumptions that we make, that express causal relations themselves. So it needs to be able to say A causes B and somehow reasons with that atom of knowledge. We have seen now in this lecture these meta-causal models that allows to model and reason over those particular facts. And in the future, we would like to have even stronger systems, maybe a combination of LLMs and meta-causal models that know why particular things happen in the real world and are able to reason about all the conditions and settings that lead to a particular causal effect emerging, or about the actions that I need to take to prevent a particular thing. We are just at the start, so it's like very simple considerations that might already be been achieved in other fields that are maybe easy to learn with neural networks and in general ML setups. But here we are really trying to systematically quantify and formalize what this reflective approach and these adaptive causal models mean if we apply them to these structural graphical SEMs. And that's it. Again, the practice exam will be uploaded, I hope, today, latest tomorrow. And yeah, next week, feel free to write in Moodle or via mail if you have any questions regarding the exam, some of the exercises. Yeah, we will do a brief recap of all of the lectures. We will maybe discuss the practice exam a bit. And yeah, then thank you and see you next week.